with the 2 from tangent. Derivative of the bottom is e to the 1 over x squared times the derivative of 1 over x squared, which is minus 2 over x cubed, like that. And we talked about before a little rearranging here, multiplying the top and bottom by the reciprocal here of this. So the way that recall that working out here, we ended up multiplying. Let's do a quick rewrite of this. 2 over 1 plus x squared, negative 2 e to the 1 over x squared over x cubed. And then we talked about multiplying by the reciprocal here. So we got x cubed over negative 2 e to the 1 over x squared, x cubed over negative 2 e to the 1 over x squared, like that. In the top here, grab it here. So come down. The 2's cancel, bring the negative to the top. So we have negative x cubed over 1 plus x squared e to the 1 over x squared. Okay, and this is still the limit as x goes to infinity. And we still have, sorry about that, this is indeterminate form at infinity over infinity. All right, so here's the problem. We know that we're gonna have to take 3 derivatives of the top and the bottom most likely because it's an infinity. So we'll do it one at a time. For the bottom, I'm gonna go to like Wolfram Alpha or pick your favorite derivative program. And I'm just gonna calculate the derivative. So you've got it. You can show the steps, later if you want, but your instructor's probably okay with you giving this without showing every single little step. Plus there's some repetition, we'll just say. All right, so unfortunately, it's really bad.
Yeah.
As we've been talking about here. And one of the problems with these calculators, and we're actually about to see it here, is they don't give you what you want. That's the derivative of the bottom. Squared like that. So having said all that, I guess we do have to do this by hand. Unfortunately, this is not going to work out the way that I was hoping for here. So scratch that. All right. Well, the issue is it's not in the form that we want. Like this is not usable in this form.
All right.
So although I'm really tempted to take a shot here at what the third derivative is.
You can rewrite the square root of e into e to the 1/2, right?
Yeah.
But then that
I take it back. It does actually give us. It actually does give us something sort of useful here. Let me do a quick graph of this on my side. I should have done that earlier. Interesting. Okay, so I've got the graph up. Maybe you've already done this yourself. Let me snip that in. Okay. So here's the graph of this. Make it a little bit easier to see. So we know the limit visually. We know that as x goes to infinity, this goes down to minus infinity. So we know what we're looking for, which is really helpful. It's almost like this should have been done at 0 instead of infinity, but that's what the instructor chose for this. So we can actually keep working out this way. I was worried we're going to have to get something, but we're going to end up getting an infinity situation here with this. So this is okay. In terms of like how you might write it, you may want to do it a little bit differently. Trying to think how the best to present this. So the top ends up being minus 3x squared. The bottom, you really want to, instead of writing this right here, you really want to keep using e to the 1 over x squared like that. And then the rest of it is okay as is. And then you can bring this x cubed up to the numerator like that. Problem is, then you got to take more derivatives. This is like an infinite cycle of stuff here.
Are you gonna put that all over the denominator?
I'm trying to see if there's something else here that we're missing. The instructor pulled this out of an integration problem, but I'm not sure why he did that. 1 over x squared. Sorry, I'm just trying to make some sense of this problem. It really doesn't, I don't like it. Don't like it one bit.
He thinks we're all nerds trying to prove it. And he's like always on
Yeah. The problem is if I rewrite it this way, you're going to have to take more derivatives of the top and the bottom. And you've now got like infinities, minus infinities, but you've got 0 here. So this actually could be enough. Okay, I think we can go with this. All right. Yeah. So this right here is the derivative of the bottom. You can rewrite it like this, and then the x cubed comes up here.
Oh, the x cubed goes up.
Yes. Into the numerator.
What?
The numerator here.
Oh, why does he go to the numerator?
You're multiplying by the reciprocal.
Okay.
Okay, so now this one over here, this one does go to negative infinity. And we can see that because it's no longer indeterminate form. Okay. No, I guess you do have to keep doing that. I'm pausing here because I keep running into roadblocks to actually doing this without having to take a million derivatives.
Right.
And that's what I was trying to avoid, is like this one here.
That's the work that I sent you from my other tutorial.
I don't know. I'm not going to take a look at it right now. So one of the things I could suggest. All right, so let me grab this.
Right.
This is, unfortunately, this is just awful. All right. So here's what we can do. We can rewrite this line, limit x goes to infinity of 1 over 2e to the 1 over x squared, like this. And you can multiply it by the limit as x goes to infinity, x to the 5th over x to the 4th minus x squared minus 1. -3, like that. So this, we took the derivative of the bottom, that's this thing. You should just write this on the right. And now we're splitting it apart. Okay, so this one on the left goes to, it goes to 1/2. All of this on the left becomes 1/2. You just have to take my word for that. The one on the right is indeterminate form. So you again have to use L'Hopitals rule. So you have to take derivatives of the top and the bottom. Okay. Now I'm not sure if you can just stop doing it, because at some point you recognize that this is a case where the numerator degree is greater than the denominator degree. Like I would just say stop and say, okay, this one goes to minus infinity. I have it. But your teacher might want you to keep taking L'Hopitals rule derivatives. Minus 60x cubed over 12x squared minus 2. That's again 0 over 0. Keep going. Minus 180x over 24x squared, like this. And then you can keep going here, limit as x goes to infinity, minus 360x over 24. And this does not go to, I'm sorry, I keep doing this. It's infinity over infinity. God bless it. So this one goes to negative infinity because the degree is greater here, and you're bringing down this 1/2. So it ends up going to minus infinity, like the graph shows. All right,
Good.
all right, B. Okay, you're supposed to make a common denominator before you start doing this. It's not in the right form. So the right form is where you multiply this e to the 1 and you take the x and you multiply it by the 1, top and bottom. So it ends up looking like this: 1 over x, e to the x minus 1 times e to the x minus 1 minus 1 x minus 1 times x times x. You're just making a common denominator. So this ends up being e to the x minus 1 minus x over x e to the x minus 1, like this. Okay. We presume it's 0 over 0, so we know to take a derivative of the top, derivative of the bottom. So the derivative of the top is e to the x minus 1. Derivative of the bottom, it's better to expand it x e to the x minus x. And then your derivative of x e to the x is x e to the x plus e to the x minus 1. Take your limit as x goes to 0 from the right, 0 over 0. Still get 0 on the top, still get 0 on the bottom. So you got to take another derivative, e to the x over the derivative of x e to the x is x e to the x plus e to the x plus e to the x. And finally, when you put 0 in, you get e to the 0 over 0, e to the 0 plus e to the 0 plus e to the 0, 1 over 0 plus 1 is 1/2. All right, I'm gonna